So this session here will be a continuation of the lecture that Arthur presented. So what we will try to do is to give you a bit more hands-on experience with some of the selected topics from Arthur's presentation. That also means that most of the time for this session here will, at least that's the plan, hopefully be devoted to exercises, and we will have a relatively fewer number of slides than we've had the previous days. We will not be presenting any new methods. The slides that we are going to present will more summarize some of the aspects from or material from Arthur's presentation that is being used in the exercises, but maybe cast in a slightly different way. But otherwise, from a theoretical side, there's not going to be any new material presented here. So what we will focus on is the part down here with Blackbox variational inference. We will only look at the score function trick or the reinforce algorithm. Here you will get an opportunity to both derive the updating equation and to make a small implementation of it, not in Pyro, but simply using the basic language of Python together with the NumPy library. Afterwards, we will move into Pyro and explore variational inference within Pyro now with the perspective of we actually know what's going on behind the scenes in terms of Blackbox stochastic variational inference. And lastly, we will touch upon variational autoencoders, where again we will do that within Pyro, and you will get an opportunity to play around with variational autoencoders yourself. All the notebooks and slides should be available on GitHub, and I should also say that we have uploaded solutions for the exercises from yesterday. They are also available on the day 2, together with corrected slides, and hopefully all errors from yesterday have been corrected and are now available. So starting with Blackbox variational inference, just to set the scene again, as you've seen several times now, we try to minimize the Kullback-Leibler divergence between our variational distributions and the true posterior distribution that we're interested in. X we use to denote our observations, Z is our latent variables. And instead of having this minimization problem, we cast it as a maximization of an evidence lower bound, which is given by this expectation here, where the expectation is taken with respect to our variational distribution. We make the standard mean field assumption. We will also deviate slightly from that today, but we'll say that, touch upon that later. But here we simply assume that the variational distribution factorizes over all the latent variables in our model, and we can treat the variables from this perspective here independently. So this part down here is basically just the Blackbox variational algorithm that Arthur presented. So we're doing a gradient ascent with respect to our elbow, and we simply iterate down here where we do perform our variational parameter updates based on our previous variational parameters. And here we have our gradient with respect to our elbow evaluated at our current point, and then we multiply it with a learning rate. And here we completely gloss over all the details about how to find a suitable learning rate and what would be a suitable scheme for reducing that. So we assume we're not going to consider that here. So the key part for the Blackbox variational inference is to find the gradient that we have up here. And the issue of dealing with that is that we are taking the gradient with respect to the variational parameters, and at the same time we are also taking expectation here with respect to a variational distribution that depend on the same parameters. So there's an issue of how to actually calculate this gradient, and this was what Arthur was mostly focusing on during this talk here. So we'll skip many of the details, and let's just say that with a bit of pencil pushing back and forth, you can change this expression to the expression that we have here. And if you're interested in it and want to do it yourself, these are the basic rules that you need to employ in order to get from the upper expression here down to the lower expression that we have here. And the nice thing about this expression that we have here is that now we move the gradient within here, so we're only looking at the gradient of the variational distribution, and that should also be taken in light of all the things that Arthur was telling you about not looking at the gradient of the model, but only at the variational distribution when you're looking calculate the gradient. And we have on the outside here, we have the expectation, again, with respect to the variational distribution. Now, if you look a bit at the components that makes up our rewritten form of the gradient, we have on the top part here, that's just the probability model that we have specified, and which is in a non-normalized version, so we can just immediately calculate that. That's easy. We have our variational distribution down here. We assume that it's a mean field factorization. It's not that important. And as Arthur said, that's something that you can easily handle, so it's not something that we pay particular attention to. Oops. Sorry. Over here we have the so-called score function, the gradient of the logarithm of our variational distribution, and again, it's the gradient with respect to the variational parameters. So if you, for instance, have that your variational distribution follows a normal distribution with mean and standard deviation, it's just like this, and you want to take the gradient with respect to the mean value, the log of the gradient you have here, then you get an expression like this. So you can just basically pre-calculate all these gradients here offline based on the variational distributions that you're interested in. It's not really something that is needed during learning. You just need to have access to these guys. Yeah. And this is also something that you're going to play around with you in just a few minutes. The expectation that we have up here, we approximate that by doing sampling. So we generate samples from our variational distribution that we have here. So we only have a requirement in order to calculate this expectation here is that we are actually able to sample from our variational distribution. Once we can generate these samples that we have down here, the set values here, then the expectation is just approximated based on the sample average that we have generated here. Each of the terms that are in here is then evaluated based on the particular sample that we have just generated. So our approach for doing black box variational inference here is to look at our elbow, and in order to increase that, we generate samples from our variational distribution. These are the samples that we generated. We use our approximation here to get an approximation of the gradient for our elbow. We perform a step in our elbow space according to a gradient ascent scheme. By that we update our parameters, our variational parameters, hopefully get an increase in the elbow, and then we perform this iteration again and again and again. This is sort of basically a very, very brief recap of what Arthur presented earlier, and there's not many more technical details to say about it at this point here. We're only looking at the basic black box variational inference algorithm with no reparameterization tricks at all. So we need to only focus on this part down here. And
so at each time step, do we sample once, only one sample, or we sample every batch of?
You can sample one, you can sample many. So this was, as Arthur illustrated with his figures, depending on how many samples you generate, the more accurate you can also get with your approximation. And this is the effect of this is what you should explore in the exercise here. So the effect of changing the number of samples, so you'll see that at least. So that's basically the introduction for the first exercise here. What we would like to do now is to work with a simple model that we have up here. So we have this is a Gaussian distributed variable xi. We have an observation of that. Xi is assumed to have a standard deviation of 1, and we're interested in estimating the mean value here. A priori, we assume that we have a mean value of 0 and a standard deviation of 1000 here. So we have a very flat prior over our mean. We want to calculate a variational approximation for that using Blackbox variational inference. And we are going to simplify quite a lot. So we assume that our variational approximation is a normal distribution with only one parameter, its mean. Its standard deviation is fixed at 1. So this is our variational parameter. And what we would like to do now is to, or what you should do now, is to try to derive the updating rule, the details that we see here, for this simple model that we have up here, and implement this part in the notebook students BPVI that you can download from GitHub. We have already provided you with, just show here. We have provided you with some help here. So first we have a part here where we generate the data. And this here is from a normal distribution that has a mean value of 10. That's quite important to remember that we already know the mean value here, and it has a value of 10. And we generate 100 points. We have here an example of how to calculate the elbow that you can take a look at when you do the updating here to see how it evolves. It's important to remember that yesterday we said that the elbow could be used as a debugging tool in the sense that if you see a decrease in your elbow, then something is wrong. This is not the case here because we're doing standard stochastic variational inference. So you can see decreases in your elbow, and that's also one of the difficulties when actually using this algorithm. But still, it's interesting to explore how the elbow evolves and get an estimate of when you will actually converge. We have here the manual estimation of the gradient for the elbow. And just to returning to the question that we had before about the number of samples, the default number of samples that you supply here is 1, but you can override that and play around with varying number of samples for generating your estimates. And then we simply have a loop here where we run over the number of samples that we wish to generate, make a sample point, and what you should do now here is to find out what are the components that makes up our gradient estimate. So we had the score function is down here, and the other part of the expression. You have the score function here that corresponds to the lower part here, and you have this expression here that corresponds to the value that you have here with the question mark. So what you should do now is to fill out the blanks that we have here, and then you will sum everything up, and we'll get a gradient estimate. If you go down a bit further, then we have the setup for doing learning, and the scheme is extremely simple. So here we do a loop with 500 iterations, and we do an elbow calculation here, just for the fun of it, and you can then restore it so you can explore it later, plot it. But the real part is just in the 2 lines following below. Here we calculate our gradient estimate based on our chosen number of samples. The number of samples that you use, you can specify that up here. And here we do our gradient ascent step. And then we simply iterate. And what you could try to do now, fill in the blanks here and try to change the number of samples used for calculating your gradients and see how that affects the performance of the algorithm. So this is sort of the task for this exercise. Any questions for this? Okay. Okay, I think I'm afraid that we'll have to move on now. But I have the impression that most of you actually got quite far with the variation, also an initial implementation to an extent. We have provided solutions for you, and they may already be available on GitHub, so you will even take a sneak peek there. But if you have already downloaded them, remember to do it again because there have been changes to it. But I would just want to go few things here with the solution. So we have the elbow here, and this was the part that you had to fill in, or you had to fill in the blanks. So for the part that we have here, the value here, that corresponds to the log term that we have over here, log of the probability model divided by the variational distribution. So this is what you have here. The part that we have here, gradient of Q, that's the score function that we have over here. And if you recall from the previous slides, we have sort of a specification of how to calculate that for a normal distribution. This is also what we work with our variational approximation, but now the standard deviation is 1. So that means that our gradient here will just be z minus mu, which over here translates into your sample value here minus your lambda value that you have here. And then we, yes, I can try to do that. Better? And then we basically just sum up. We have the sum gradient estimate that keeps track of the sum that we have out here. And in each iteration over our set of samples, we multiply our gradient with the value. So we multiply this guy, our score function, with this guy here, sum everything up, and in the end we divide with the number of samples that we have corresponding to the m that we have over here. So that's sort of the setup. And if we use that, we can now try to play around with the effect of, I'm just starting this here. So the code that I have here, it's not quite the same as you have in the student notebook. So what I try and specify up here is to let's estimate our gradient using different number of samples. So 1, 2, 3, 4, 5, so that's the m value that you have out here, up to 50 samples. And then I estimate my elbow for each of the samples, and then I do my gradient ascent. And what we can see here, and I'll say a bit more about it just afterwards, the results are shown down here. For each line we have the result of performing gradient ascent using a specified number of samples. Our starting point is Q mu equals minus 10. And if you recall, we had specified that our sample data was generated with a mean value of 10, so we are pretty far from our starting point. This here is the estimate that we get with our variational distribution. This here is the error in percentage, and we have your calculation time out here. So what we can see, and this is also a bit what Arthur hinted at, you can, in some cases at least, get some improvement if you use more samples, but you're also starting to be, it also going to be more and more time consuming. And all this has to do with the variations that you get, the variance you get in your gradient estimate. And we can explore that a bit further. Well, first of all, we can take a look at the elbow, how it changes. So this here is the evolution of the elbow if you use one sample for estimating your gradient. So here it actually looks pretty nice, but you can also see here that you don't have sort of a monotonically increasing function. You actually have some decreases from time to time, but again, that's the result of the gradient ascent rather than coordinate ascent. And we can also here explore the effect of using different number of samples, and there are still changes or decreases in the function here. If you use 50 as I talked about, it becomes a bit more smooth, but still you can see that there are sort of these minor fluctuations where you also maybe decrease. We can also explore the estimate of the variation in our estimate. And what I've done here, or what we've done here, is to look at we use this number of samples for estimating our gradient, again our m over here. So we look at what happens if we use one sample, two samples, up to 25 samples. For each number of samples, we generate 500 different number of samples over here. So we have, for instance, for 5 samples, we generate 500 different gradient estimates. and then we can see how that varies. And if we notice, what we've done here is also to fix the current lambda value to be 9. We would like to have it sort of close to 10. So what we would like to see here is that the gradient should be positive, because we would like to move it from 9 towards 10. And if we plot the density curves for our gradient estimates using the different number of samples that we have here from 1 to 25, these are the curves that we see. So the general picture is that if you have more samples, you are more inclined to be to the right of 0, so a positive gradient, which is nice because we would like to move in a positive direction. We are at 9, we would like to move towards 10. But you can also see here that there's a significant number of gradient estimates that are actually going in the opposite direction. So this is also sort of a one-dimensional illustration of the two-dimensional plots that Arto showed you before lunch, where you could actually move in the completely opposite direction of where you wanted to go in. And it's the same thing that we see here. So it's really a big problem, and you can, to a certain extent, mitigate it by increasing the number of samples, but as you can also see here, you are not completely safe. Yes?
So this first experiment that you showed, where you vary the number of samples,
Yeah.
at some point the error actually increased, even though you have more samples. So
Yes.
That's something good that is just a coincidence,
We generate different, for each run we generate different samples. So there is a natural variability.
because it looks quite systematic.
Yeah, I don't think there's sort of an...
I think you run it again, you may end up with a different.
Yeah.
Different
Because
shape.
there is something there just like. Yeah, no, it's
Let me do it.
And also you, for example, with it.
So there are... Sorry? So you can see there are some variation in it. Do you want to add something to this, Andrés?
Yes. I think even if, yes, the question is with one sample, we make the estimation of the gradient with only one sample. Okay, you may be lucky sometimes, but you may.
Oh, it's the same value, you need to run it.
Exactly. Exactly. But it may change a lot. With samples, you may be lucky and get a very nice increase in the elbow, but you may be quite unlucky and may have very deep decrease in the elbow. However, when you do it with a much more samples, you usually get a very steady increase in the elbow. Okay? It's something that you will see.
And this is also what should be captured if you look at the density curves over here, that you are more likely to go in the right direction here, but no guarantees. And again, you can see significant decreases in the elbow also as we move along. So this was just an illustration of, another illustration of the examples that Arthur gave you previously here today. And the key part here is to do variance reduction. And we saw different ways earlier to do that, particularly with reparameterization tricks. And there's also the issue of doing implicit reparameterization. But again, it's something that we are not going to cover here today. So this is just to illustrate the problems that you may run into and which you need to be aware of. Okay, so now we will move into probabilistic programming and in particular using Pyro.
Yes. Well, the idea now is like, well, you have now an idea of this variational inference. You have an idea how Blackbox variational inference works, which are the underlying principles, which are the main techniques. Okay, now we are going to see how we can really deal with variational inference when we have a probabilistic model and we want to code it in Python. On day one, we were working with different probabilistic models. Simple models, sensor temperature measurements. There were other models, Bayesian linear regression. Okay, but we didn't care about these kind of guides. I don't know if you may remember. Okay, now in this part of the tutorial, we are going to work on that. And we'll see how does it work in Pyro. and we will finish with a code exercise for defining guides. So just to recap, so in Pyro we can make modeling, okay, having directed graphical models, in combination with neural networks. We will see more about that later. We have different inference engines, mainly variational inference based on Blackbox variational inference. We also have Monte Carlo, like important sample, Hamiltonian, all of them are variational engines that are available in Pyro. And we can also make evaluation, okay, of our variational posterior. So the question is, this is a very basic example of a model in Pyro. We worked on that Monday. The question is, I have this random variable, which is the temperature, the real temperature that I may have in this room, okay? But this is a latent variable, so I cannot really observe this temperature. What I can really observe is the value that is given by a sensor measurement. Okay? So the sensor measurement is will provide me a value which is follows a normal distribution, which means the real temperature of the room plus an error measurement. Okay? So now, if I get an observation from my sensor, I can just include this observation here. Okay? So remember, we have this Pyro.sample construct for defining random variables. Here I define the distribution. Okay? Some of them may be latent, and some of them may be observed. Okay? And we define our model in a Python method. Okay? The next thing now, the guides. Every time that we define a model in Python, we have to provide a guide. The guide is used to produce samples for those random variables in my model that have not been observed. The question is, these guides are used, in the case of variational inference, they are used for defining the Q distributions, okay? The variational approximation, that it can be used in another inference setting. For example, in important sampling, we'll define the proposal distribution. And, for example, that can also be used to implement inference networks, like the ones that relate to what Arto explained this morning, to implement this amortized inference. We'll view something about that later. Okay? So the question is, when we define in a guide in Python, so first we define our model, and then we define our guide. There are some criteria that has to be met in order to define a proper guide within Python. The first one, the signature of the model and the signature of the guide should be exactly the same. Okay, they should have the same input. Perfect. And then, for every random variable in our model, in this case, we have two, but only this one is latent. Okay? There is no observation associated to this one. We have to create another random variable in Python. Okay? Which has, this is important, has the same name than the random variable that I have in my model. Perfect? So in that case, the distribution, they match. Okay? But it can be different. Okay? So as you know, when we are defining a variational approximation, a variational distribution, okay, we need the variational parameters, which are the ones that are optimized in order to solve my inference problem. So the parameters, so this variational distribution for the temperature, okay, follows a normal distribution. It has a mean and a scale, mean and standard deviation. Perfect. Then the mean is a parameter that is going to be learned by the inference engine. So we define it here using the Python construct. Okay? So we give the name, and we also provide an initial value for this parameter. Okay? The only parameter for defining the variational distribution, B, which refers to the standard deviation of the variational distribution. So we also define it, okay, as a Python param, something that is going to be there. We provide the initial value here, 1. Perfect. In Python, all initial values should be provided in the form of a tensor. This is because we have to do it like a tensor. Okay? And the question is that the scale, okay, when performing the optimization, okay, the scale is constrained, has always to be positive. Okay? So then in Python, it's quite easy to deal with that, because here when we define the parameter, so we can explicitly speaks about the constraints. Okay? So we explicitly say that this parameter has to be always positive. Then we don't end up in an invalid solution. Okay? So now we are going to see, okay, the Bayesian linear regression that we were working the other day. It's a notebook which is available in the GitHub repo. It's exactly the same code that we have the other day. Perfect. But the main difference now is, remember we downloaded the data, okay, something to say about African nation, the ruggedness, the geography of the African nations, non-African nations, the relation with the GDP, okay. This is the Bayesian linear regression model that we are going to work with. Perfect. This is the definition of the model. You can see here that we have the weights. Perfect. In this case, we have 3 weights, which are initialized with a normal distribution whose mean is 0 and which standard deviation is equal to 1. Then we have the intercept, okay, B. Then the intercept is also defined, so the value of the intercept is defined as a normal distribution, which is mean is 0 and this deviation is 1000. So the question is, we introduce here 1 in order to induce a regularization over the weights. We really want that the weights to be close to 0 as possible, as small as possible. Okay, this is a standard regularization that can be equivalent to L2 regularization when you are doing a standard approach for linear regression. Now we define the precision. Okay, in this case the precision follows a gamma distribution. We correspond to this one. And then we define the mean observation, which are the y here, okay, who follows a normal, whose mean is just the linear combination between the data and the weights plus the intercept, and the standard deviation of this normal distribution follows this equation, which depends on the precision. The standard the variance is the inverse of the precision, but we have to work to the standard deviation, so this is because we introduce the square root. Okay? Now we have this is how we define our Bayesian linear regression model, and now we go to define the guides. Okay? We have provided 2 guides here. I'm going to try to make it a bit bigger. Mean field guide. Okay? So we have our latent. The latents are the weights, the intercept, and the precision. Okay? They fully factorize all of them. Okay? So we have, let's see, we have here exactly. We have here we define the Q over the weights, over the intercept, and over the precision. Okay? These 3 ones. When defining the Qs, we have also to attach the parameters. Perfect. So we define the Qs for the weights, which is a normal distribution, and these are the 2 parameters that are defined up here. We define the Q over the intercept, which is a normal distribution, who has 2 variational parameters, which are defined over here. And we have defined the Q over the precision, which follows a gamma distribution, who has 2 parameters, which are defined here as well. Okay. This is a way to define the Q distribution in terms of guides within Python. Okay. If you go back to day 1, perfect. You go back to day 1. Let me see. I think we can go back. Just a moment to day 1. Yes. And day 1 for defining the guides. Okay. We have. A moment. Perfect, can you see? When we are defining the guide, in Pyro we can use also what is called AutoGuide. Okay? So in case you don't want to go and define the guide by yourself, okay, you can use this AutoGuide functionality here, okay, and it will build this method in an automatic way for you. Okay? And then you use the control when defining the guides. And there are many cases when you have to define the guides by yourself. Okay? But there are many cases which is quite standard. It is standard enough that can be done with this functionality. You can do that, and you can avoid all the process of defining your guide. But in that case, we just wanted to let you know how to do it manually. Okay? And this is how the code for defining the guide looks like. We will give you some time later, then you can really go through the code and play around with it. Okay? So what if we want to define, for example, a generalized mean field approximation? No? So now we have our posterior, okay, over the weights, the intercept, and the precision, just factorized. But this part doesn't fully factorize. Okay? So what I'm going to do here is just to introduce for the weights, okay, a multivariate normal distribution. So we can do that. We go to the guide, and we define in the cube, we introduce a multivariate normal distribution instead of a bunch of normal distributions. There is some technicalities here where when we define we have the multivariate normal distribution have two parameters, the mean and the covariance. Okay? The problem of the covariance you have to guarantee that it's always positive, semi-definite, semi-definite, okay? In order to be invertible, you know? So this is again a constraint optimization problem. Then in order to get rid of that, what we do here is to express the covariance matrix as a triangular matrix, okay? Using a lower Cholesky factorization. So the question is, here we define a lower triangular matrix, which is the scale, okay, doing constraints, and then when parameterizing the multivariate normal, instead of specifying the covariance matrix, we can specify, only the lower triangular matrix. And then multiply then the covariance matrix inside the covariance matrix of this multivariate normal distribution will be built by multiplying this lower triangular matrix by a transpose of the same lower triangular matrix. This is a standard factorization. And then we can run inference. We can just switch from one guide to another. We just perform standard stochastic variational inference. We just follow the gradient using a stochastic gradient ascent. Okay, this is the result of the optimization problem. So the optimal variational parameters. And now we again get back to the same solution that we saw on day one about, well, when we are Bayesian about a linear regression model. Perfect, so we don't get a single regression line, but we get a bunch of regression lines in the sense that we are able to capture uncertainty in our model. Okay. We have done the same for factor analysis. Okay. So let me show. So you have a factor analysis model in order to perform dimensionality reduction over n is data. Perfect. So there is a notebook there. So the factor analysis model that we have been working with it the day before is now coded in Pyro. Okay. We define the guides in Pyro for the factor analysis model. Okay. And all of the details are provided here. So the idea now is that you go, have a look at the Bayesian linear regression model, okay, at the factor analysis model, just to get a feeling how to define guides in Pyro, okay, and you try by yourself to implement a simple Gaussian model, okay, the model of a Gaussian distribution, okay, Bayesian set is when you have a set of samples which are normally distributed, given some mean and some precision value. When the prior over the mean is a normal distribution and the prior over the precision is a gamma distribution. You define this model, and you should also define by yourself the guide of the model. Okay? Just remember, when we define a guide, okay, this is the easy part, the model. When we define the guide, we have to provide a distribution, pilot sample, for every random variable in my model that has not been observed, which is not observed. Okay? We define this random variable temperature because this random variable temperature has not been observed. It's also observed the sensor marker. Perfect. Then the variational distribution has the variational parameters. Okay? So we have this variational distribution, it's normal, it has two variational parameters. And the variational parameters are specified using param constructs. Okay? You give it a name to the parameter and initial value. Perfect. And also you provide constraints for those parameters that are constrained. Okay? So go to the notebooks, okay, have a look at the Bayesian linear regression, just for having an idea how it works, also for the factor analysis, having an idea about how it works, okay? And then also go to the exercise 2, to this notebook over here, okay? And complete the exercise in order to code a Gaussian model, okay? Also the model and also the guide, and see that everything works properly. So you have an issue there, raise your hands, okay, and we can help you out. I think this is should be an easier, far easier than the previous exercise. Okay? Well, here you have the solution for the exercise. Okay? So the solution for the exercise looks like that. I will try to go through the solution and try to explain it. So the question is, so we have observation X. Okay, so the observation follows a normal distribution. Perfect. The question is that we have a bunch of observations. In that case, we should have a bunch of random variables. So we do that by introducing the plateau. Okay? Plateau replicates these random variables multiple times. As many times as we have data. Okay, as many times as the number of samples in the waiting set. Perfect? So our samples follows a normal distribution. The question is, this normal distribution has a mean and has a standard deviation scale. Okay? The question is, I don't know the mean of my normal distribution. Perfect? Because I don't know the mean of my normal distribution, because I have a Bayesian guide, I'm going to define a prior distribution for the mean of my Gaussian distribution. Okay? So I define another random variable that represents my uncertainty about the mean of this normal distribution. Obviously, I have a single mean. This is because this guy is not within the plateau, it's outside the plateau. Okay? Then, again, the mean of my normal distribution, okay, is a random variable that follows another normal distribution. Okay? But this normal distribution has some given parameters, okay? Which is, I guess, is centered around 0 and very large standard deviation. Okay? So it's like almost a flat prior. Perfect? We represent my beliefs where this mean, when the mean is located, which is everywhere. It can be everywhere because it has almost a flat prior. Okay? So then it happens the same with the precision. Okay, gamma. Perfect? The precision of this normal distribution, okay, which is here, I have to do this trick because in order to parameterize a normal in Pyro, I have to provide always the standard deviation. The problem is I have to do, I cannot provide directly, I can provide this, the prior over the standard deviation given an inverse gamma, but the inverse gamma is not coded yet in Pyro. This is because I have to give the prior with the form of precision and then move from the precision to the standard deviation through this equation over here. Okay? So I have to. But the question is, I don't know the precision of my normal distribution. Reminds, the precision is the inverse of the variance. Perfect. So the precision, because I don't know, I'm going to use a random variable to represent this uncertainty that I have. When I'm in a probabilistic modeling approach, where I don't know anything, I just include a random variable. Okay, that's all. I don't know the precision, I include a random variable. I don't know the mean, I include a random variable. Okay? Then I have my model, my generative model. Okay? This is the generative model, the P. P of X and gamma and mu. Perfect? And just for fun, let's see. I'm going to go back here, okay? Yes. So the question now is, I have my data and I have the latent. The latent are the mean and the precision. Perfect? So what I want to compute is the posterior. Okay? The posterior will be, it's not just a point estimate. It will be a guess where the mean really is. Okay? The optimal solution is a distribution or the possible values of the mean of this Gaussian. Okay? So this is what I'm trying to look for. Okay? Perfect. The problem is, I cannot compute this line. I cannot compute this posterior. Okay? We are in a Bayesian setting. What I'm going to do is to define a different variational distribution Q, which is going to give me an approximation to the true posterior. Okay? Perfect. The question is, this Q distribution depends on a parameter. Okay? Lambda, some value. Okay? Then, given a lambda value, I will have a distribution. Okay? Over the mean and another distribution over the precision. Okay? But that distribution can be very bad. Perfect. So what I really want is to move the lambda parameter, okay, to find the Q, which best approximates the true posterior. Okay? And then I'm going to move that, I'm going to move this lambda, okay, using gradient. Perfect. The question is, I have to define this Q. Okay? How this Q looks like. This is what I can do in Python. Okay? Remember, the Q is over the latent. So here I have two latent variables. One is gamma, another is mu, because X have been observed. Okay? So it's observed. Okay? So the latent, the things that I don't know is the mean and the precision. Perfect? Then I have to define a Q over the latent, which is a Q for the precision and another Q for the mean. Okay? These Q are random variables, and they are defined with the same construct in Pyro, Pyro.sample. Okay? Then the Q over mu is a normal distribution, and the Q over gamma is a gamma distribution. Perfect? But this Q can be anything, any gamma, any normal distribution. Okay? Why? Because we have these lambda parameters. Okay? Perfect. So I have to define these lambda parameters. The normal have two parameters, the mean and the scale, okay, or the standard deviation, and the gamma have two parameters, the rate and the concentration, which are these two parameters. Okay? Parameters means values. It can be also vector matrices, whatever. This means just value. Okay? So I define these values using the Pyro param. Perfect. And then I have 4 different variational parameters. 2 for defining the Q over the mean, and another 2 to define the gamma over the precision. Perfect. So the next thing is Pyro knows that these are the free parameters. They are free parameters that it can optimize. Okay? So Pyro will try to optimize these free parameters, okay, using variational inference, using gradient ascent over the elbow, computing the gradients using the Blackbox variational inference approach that we have seen this morning, okay, in order to find the lambda that defines this Q that best approximates the two posterior in terms of urban layer differences. Perfect. So you always have to consider which is my model, P model, and which is my Q model. Okay? And remember, the Q model has parameters. Okay? And these parameters are going to be optimized. We are going to find the optimal parameters, the optimal numbers for this guy, for this guy, for this guy, or for this guy, that make that this Q, okay, this guy and this guy, are as close as possible to the posteriors, okay, to the true solution of our problem in an approximate way. Okay? Sorry, well, again, through that, just in order to have a very clear example how that's translated from one way to another. Okay? So that's the idea, okay? And now here you have the learning, here you have the elbow, here you have the result, and then you plot how you can plot how the elbow evolves. Okay? And the coverages. Yes. Exactly. So the question is, okay, yes. Wow, I forgot it. Thank you. So actually, these two guys, it may work, it works in that case. Constraints of positive. So, this should be positive, this should be positive, and this should be also positive. Just for sake. Okay, so
you have a type though.
Okay. Well, now I'm going to go to the factor analysis example. Okay? In the factor analysis sample, so this is going to be like an introduction to what I'm going to talk about later, which is variational inference. Okay? So factor analysis, what it's going to makes the following. So it's a dimensionality reduction model. Okay? So in my case, I'm going to treat, I guess I'm familiar with the MNIST dataset. Is there anybody which is not familiar with the MNIST dataset? Okay. MNIST dataset. So MNIST dataset is a database, okay, of images of handwriting digits. Okay? Perfect. So a handwriting digits has a 28 by 28 pixels. Okay? So when we translate to a vector, this means that we have 784 dimensions. Okay? So I have any digits, any image is a 784 dimensions. Okay, so I have 784 floats, values to represent my digits. Okay? Then I'm going to compress that only in 2 dimensions. Okay? So the dimension of this guy is 784, and the dimension of this guy here is 2 dimensions. Okay? And this compression is going to happen through the weights. Okay? This weight is going to define how the compression is. Okay? But it's also at the same time a generative model. Okay? So, given 2 numbers from here, I'm going to sample an X, which is going to be an image, 28 by 28. Okay? Given an image, 28 by 28, when you compute the posterior over this guy, I get 2 values. Perfect? So this is because can be seen as a dimensionality reduction. So I can transform any of the digits I have in 2 values. 784 numbers to another 784 numbers in another. Okay? So the next thing is that we can define this model here. I will go quick for that. Okay. Perfect. Like this is the X, this is the Z, and these are the weights. Okay. Then the guy. So So I will go back here again. Observe, latent, latent. Okay? Observe, latent, latent. Okay? This guy within the plateau. This guy outside the plateau. Then I go to the guide. Then the guide will have one for the two latent weights and another for the set. Okay? These are the two latents. Okay? And the parameters. I perform learning. Okay? And I have to say sorry because this is like that. Let me fix that. Okay, sorry. No, because now there is a minus here, okay? Just in order to see that the plot goes up. Okay. The question is that in Python, it's always everything is done in terms of loss minimization. Okay? Why? Because it relies on PyTorch, and PyTorch only understands about loss minimization. Okay? Actually, what you define here, the stochastic variational inference is in terms of a loss. Okay? So just in order to make it compatible with what we have seen in these days, so we just plot the minus of this loss, and then we can see, okay, so what happened here is like getting a set of plus, 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 until I get the better parameters, the parameters of my model that best explain my data. Okay? And this is the result. Okay? These are the parameters, but the important thing will happen here. Okay? Perfect. Yes. This is the encoding, the dimensionality reduction for all the digits that I have in my dataset. Okay? In this case, in order to make things quicker, we just select 3 digits, okay? Because otherwise the MNIST dataset is quite big, and then the learning will take a lot of time. Okay? We just set 3 digits. So 3 digits, 100 samples for each one. Okay? So each digit is just projected in a 2-dimensional space. Okay? So we just assign a color, okay, to each of the digits. Okay? So the question is, as can you see, okay, for example, all the 7 digits are more or less clustered together. All the digits 5 are clustered together, and the digit 6 are also more or less clustered. Okay? And this is something that is done without supervision. So the model didn't know anything about the label. Okay? The model just tried to encode similar objects in a similar hidden space. Okay? So it has been done without supervision. Okay? And then we can see that it works. Perfect. Exactly. This is usually what people do is like, I have a very high dimensional objects. Okay? If I play clustering there, usually it's not a good idea. Okay? Why? Because the distance, especially the Euclidean distance between 2 digits, for me, okay, this is how it may work, but there is another guy who will make something like that. Okay? Then the Euclidean distance of these 2 guys can be very large. Okay? However, when I take the Euclidean distance of the projection of these 2 guys, is very close. Okay? Which makes that the clustering algorithm works much better in this low dimensional space than in the higher dimensional space. Usually people do that a lot. Okay? The question is the following. Is now, so can you see there is lack of, they are not very well separated, isn't it? Yes. So why? Because I'm using a factor analysis model. Well, sorry, this wasn't really a factor analysis model, okay? Because a factor analysis model here has a normal distribution, okay? But I use a binomial distribution. Why? Because my pixels are not 0 to 255, are 0, 1, okay? It's like binarized MNIST. I have 0, 1 values for my pixels, okay? Now I can use binomial to model this 0, 1, okay? Which is the problem? The problem of the binomial is this is a model, when you place here a binomial, this is a model which falls outside of the conjugate exponential family. Okay, so we have to use a specific variational inference. Okay? One question. Another question. The relationship between Z and X, can you see? Is just a linear relationship, it's a matrix multiplication. It's a linear relationship. Okay? The question is that people have realized that linear relationships in some data spaces are not powerful enough. Okay? Which is this kind of data spaces, especially those that have to do with images. Okay? In images, linear relationships works very bad. Okay? What works very good with images? Deep learning. Okay? And which is deep learning? Deep learning are non-linear transformation. Perfect? So what I'm going to show you now is how to replace this relationship between Z and X, okay, instead of a linear relationship, matrix multiplication, with a non-linear relationship, which means a deep neural. Okay?
So what is this 2-event?
Sorry?
2-event.
Okay, the 2-event, this is like a special thing that we have to do in Python. Okay? It's a bit tricky. It's one of the things, it's a bit technical to Python. Okay? The idea, I will try to explain the idea, this is something that has nothing to do with what I said before. Here I'm defining a bunch of normal distributions, okay? I provide a matrix of zeros, number of attributes by number of layers, okay? And then defining a bunch of independent normal distributions, okay? But Python doesn't like that, okay? It has to be a single distribution, okay? So I have here a bunch of independent distributions, and then by doing these 2 events, I transform this bunch of independent normal distributions in a single multivariate distribution. Perfect? You have always to do that. You always have to have a bunch, you define a bunch of independent normal distributions, you have to add these 2 events in order to transform in a single multivariate distribution. Otherwise, Python will give you an error. Perfect? There is, if you go to the documentation of Python, okay, you will find very, okay, it's not easy to understand, okay, it requires, perfect? Okay, then we are going to move to what is called, sorry guys, variational autoencoders. Variational autoencoders, as I told you, is a way to define, to code, okay, again, images, an image, an object, in a lower dimensional space, okay? But using non-linear transformation, it means deep neural networks. Which is the nice thing of that? It means that the relationship between this guy and this guy is going to be expressed by a neural network, okay? Arco has been speaking about that before, okay? And thus places us within the field of, which is called deep Bayesian learning. Deep Bayesian learning is I have my Bayesian probabilistic models in a Bayesian way, okay, and I try to add deep stuff inside in order to make my probabilistic models much more expressible and much more powerful. Perfect? And this is like a new field of research right now, trying to merge deep learning with Bayesian learning. Okay? This is because Google is developing TensorFlow probability, Uber is developing Python, okay, because they are trying to get the best of both worlds. Why? Because, as you have maybe know, I mean, deep learning is having some limitations. Okay, have some limitations that are hungry. I mean, the answers that give you deep learning are not necessarily have any uncertainty associated, so for many specific problems, that can be really relevant, okay, but I'm not going to go into that discussion now. But the question is, I have this model, and I'm going to try to put deep neural networks inside, okay? The thing is, this X given set follows a Bernoulli, okay? And the parametrization of this Bernoulli, okay, the logics, depends of set, but through, okay, a function. Okay? And this function is a deep neural network. Perfect? So you saw that this morning. Okay? And this is in the P model, okay? In the P model. Okay? But I also have the Q model. Okay? The Q model will give me this connection over here. Okay? Given an X, will give me the projection in two-dimensional space. Given an image, it will give me the projection in two-dimensional space. This projection is the posterior distribution, okay, over Z given X. Okay? And this posterior distribution over Z, over the latent given of Z, okay, is the posterior that we cannot compute, and because we cannot compute, we need to place a Q distribution. Okay? How looks like this Q distribution? Mainly the Q distribution, what it's going to have, okay, this is the connection Z given X. The Q distribution is going to be another function, H, okay, will give me the mean and the precision, okay, of set, okay, which is known. And this H is also known and the encoder network. So in this variational encoder, we have two networks. The one that connects set with X and the one that connects X with set. Perfect? So the question is, in the model, where do we introduce the decoder? The network that connects this guy with this guy. In the model or in the guide? In the model. Perfect? The connection of this guy with this guy is in the model. Okay? The generative connection. Do you understand? Then the generative one is in the model. This is because the decoder, okay, which is the network that connects this guy with this guy, decoder because you have a low-dimensional representation and it gets expanded in a high-dimensional representation. You have the hidden code, which is decoded in the real part. Okay? And now you have the inverse. You have a large object that you want to codify in a small representation. Okay? That means that the information goes from here to here. So I'm going in the inference part. Okay? I'm trying to compute the posterior over set given an image. Perfect? Then the information goes in the other way around. This is posterior inference. Posterior inference means that we have to go to the queue. Okay? And the queue is specified in the guide. Okay. Just remind that. Okay? Well, the question is, we specify P, the model, we specify Q, then we go to Pyro. Pyro makes a lot of, right? Can you see inference? Like sample from the queue, compute the gradient, update, sample from the queue, compute the gradient, conversion. Okay, that's the properties. Perfect. So we process the MNIST data, okay, with this network. And we have this, the encoder network, we have this architecture, okay, like bunch of, this is like the input, 784 dimension, we have a ReLU, hidden dimension, ReLU, hidden dimension, linear transformation, we get back the mean and the variance over the queue of set, and we also have the decoder, okay, which goes from set to X, okay, also through non-linear transformation. Perfect. So you can define any architecture that you want in order to define this connection between the X and set and X. I remind you that everything is probabilistic. Okay? The connection is just defining the parameters of a probability distribution. Okay? This is a variational autoencoder, not an autoencoder. Perfect. So you perform learning, as I told you before, and this is what you get. So one thing I can do is the following. Okay? I have a 5. I compress the 5, okay, in 2-dimensional. Okay? And then I can use this 2-dimensional representation to generate another 5. You see? I have a 5, I compress it, and then I use the decoder network to generate another 5. Okay? At the beginning, this is how it looks like the generated 5. Okay? It's nothing to do with this one. However, when I learn, can you see? So this 0 is quite similar to the generated 1. This 8 is quite similar to the generated 1, and the 2s are quite similar. So it means that I have a good coding scheme and a good decoding scheme, okay? Because I'm able to go back. Perfect. And then this is like the hidden dimension, the hidden representation, okay, of the 10 MNIST, of the MNIST numbers. So here I don't plot the points, I just plot the density curves, okay, of the hidden representation of the numbers. Perfect. As you can see, the hidden representation of the 7s are all of them just separated. Okay? And this is an information that is not, there is no supervised information for this model. This model has find a very nice hidden representation, 2-dimensional representation of 784 dimensional objects, which are each of the MNIST images. The difference with the example that you saw before is now we are using in order to go from one hidden dimension to the observed dimension, okay, for the hidden representation to the observed to the real representation, we use deep neural networks. And the nice thing is that Pyro, all these black box variational stuff, okay, are able to deal with this kind of mixing probabilistic components with deep neural network stuff. Okay? But you will learn much more about that the following 2 days when you go to the part of deep generative models. So we just wanted to give you some kind of overview on how this model works. And now, the last 10 minutes, you can go to the notebook, which is called VAE, okay, Variational Autoencoder. Open it, okay, and then you will find there how to code a variational autoencoder within Pyro. Okay? Remember, the coder network is in the model, and encoder network is in the diagram. Okay? We have done that over a very small MNIST data sample, okay, just in order to make things run quicker. We have used a very simple neural network architecture in order to make it quicker, okay, but play around and then you will see at the very end, okay, how it's able, you know, to set different keys apart, okay, by building making a dimensionality reduction from an image to a two hidden dimensional space. Okay? And all of that can be done in Pyro quite easily. Okay, well, quite easily, with that. Much lower level of complexity than was possible before. Okay? So just play around this notebook and let us know if you have an issue over there. Okay? There is any exercise here just to play around. You can just change maybe the architecture of the neural network, adding more hidden layers, making it smaller, changing the learning rate, and just see what is going on down there, trying to understand the code, and everything.
Okay, so it seems that we are running a bit out of time, so I'll just end this by coming with a few closing remarks before coffee and then the next lecture. So what we try to cover here with this tutorial here is to give you a sort of a bit of a hands-on introduction to variational inference and probabilistic programming languages. And what I hope that you've gotten out of it is sort of, in terms of take-home message, is that probabilistic programming languages offer you a very flexible and expressible tool to rather compactly and easily specify complex models, combining both standard probabilistic constructs and deep neural networks, for instance, like Andrés showed you just before. And we have powerful inference engines to actually to support inference in these types of models. Most tools also supply other types of inference besides variational inference, like Monte Carlo, Antonio Monte Carlo, and so forth. We also looked at ways in which, if you work within the conjugate exponential family, that you can actually perform variational inference in a coordinate ascent kind of fashion, where you don't have to work with the gradients that we've been looking at today. This also means that you could do variational inference much more efficiently, although it's under the constraint that you can't fit yourself within this type of model class that we're working on here. We were spending a bit of time trying to do these coordinate ascent updating rule by hand. And indeed, as was pointed out several times, it's error-prone and tedious and all that kind of stuff. But there are also tools to automize that process. So, on top of conjugate ascent and coordinate ascent variational inference, if you embed your distributions within the exponential family that Arthur described earlier, you can also have some flexible and generic inference mechanisms that relies on a message parsing scheme within your models, also known as variational message parsing. These tools or methods are also implemented in toolboxes like Infer.net from Microsoft, or another recently proposed toolbox called the Bits toolbox that we have been working with as a developer there. And we also looked at these, if we go beyond the conjugate exponential models here, that we're actually able to combine these powerful techniques from deep learning community with our probabilistic models. We can work in a very general fashion using Blackbox variational inference, but we also see that there is uncertainty or there is a lot of variation in the gradient estimates that we get using Blackbox variational inference. So one should also be a bit cautious with using these methods here. On the other hand, it also works well in many cases, especially if you could use these more refined versions of doing gradient estimates, like for instance using your minorization tricks, which we didn't cover in this tutorial here. So, take-home message is that we have a bunch of tools available that provides you with a lot of power in terms of defining your own languages, and also offers you powerful inference engines in which you can actually do inference and learning of these models and data. So that was it from us. So I hope that you've got a few things out of it, and otherwise you also feel free to play around with the notebooks, and if you have questions about what we put up, then drop us an email and we'll try to see if we can answer it. Okay. Thank you.